Today I'll be talking about my team's development of a mycopesticide for lesser mealworm in meat chicken sheds. Lesser mealworm is the predominant insect pest of meat chicken sheds worldwide. It's also known as darkling beetle or litter beetle, and it's a bit of a problem because it carries a number of bird and human pathogens, and it also damages the shed floor and walls. It's also known to interrupt the feed conversion rate when the birds eat the beetle in preference to the feed. Lesser mealworm ecology inside meat chicken sheds is pretty well matched to the meat chicken system. At the beginning of a chicken flock, the adult beetles emerge from the floor of the shed and populate the litter where they lay eggs. Those eggs hatch into young larvae which move through the litter and congregate in areas that we think are protected from chickens, particularly underneath feed pans. As those larvae mature over the coming weeks in the batch, they start to tunnel into mostly the floor where they pupate again. Those pupae will emerge in the next chicken batch and repopulate the litter. There are a number of control methods currently for lesser mealworm, and pretty much they're all chemical based. Unfortunately, there's a lot of insecticide resistance. It's pretty strong and widespread throughout lesser mealworm populations in Australia. There are some other husbandry practices that help with lesser mealworm numbers, such as litter composting and removal. We know that if you have a hard floor, then that's probably the best method for controlling beetles. The populations in those sheds are pretty low. Research has shown there are a few other methods or agents that could be of use for controlling lesser mealworms, such as nematodes, inert dusts such as diatomaceous earth and lime, natural oils. Most of those have had some success in the laboratory and a little bit of success in the field, but probably the most promising new method or novel method is entomopathogenic fungi. So what are they? Well, entomopathogenic fungi are natural pathogens of insects. There's a number of types worldwide, about 1,600 species. Most of them are only weakly pathogenic to insects. So there's a particular two which are particularly good for insect control because they're easy to produce in the laboratory. They have relatively broad host ranges, and they're easy to apply. The way entomopathogenic fungi work is that the spores of the fungi, known as conidia, adhere to the insect surface, they germinate, and then over a few days they penetrate the insect, grow through the insect's body, release toxins, and kill the insect over a few days. When you take entomopathogenic fungi and turn them into a pesticide, they're known as mycopesticides. There are different types. You can make them into wet formulations with oil or oil emulsions, and they're good for spraying over large areas such as crops. Dry formulations such as dusts or granules are good for scattering or incorporating into soil. There are about 170 products registered worldwide with entomopathogens as the active ingredient, and most of those are done with those two fungi, Metarhizium and Bovaria. So the advantages of entomopathogenic fungi are they occur worldwide anyway. They're safe to birds and mammals. The right species can be cost effectively mass produced. There are no known resistance issues in the field, unlike chemical insecticides, and they don't leave any residues in the environment. There are a couple of disadvantages. One, generally you have to match a good fungal strain with your insect pest for good virulence. They definitely need a moderate temperature, 20 to 30 degrees, to be effective, and highish humidity. And they're a little bit slower to cause mortality. It takes 3 or 4 days at the right dose rather than, say, a day or a few hours for insecticides. So in my first AgriFutures Australia project, we were looking at developing mycopesticides for lesser mealworm control. We looked at Metarhizium and Bovaria, and we found that we could use a granular formulation of those and achieve greater than 90% mortality on the larvae within 7 days. We also looked at how the granular formulation could be applied in a chicken shed and found that it was pretty much compatible with the chicken shed environment in terms of pH, moisture content of the litter and floor, and that an application to the floor was probably in line with the current methods used for insect control in broiler houses, which do rely on spraying empty sheds. In order to produce fungi for a field trial or for a full broiler shed treatment, we used a nutrient broth biphasic system where we were able to grow fungi as a nutrient broth, apply it to a substrate, dry that substrate, and then harvest conidia or spores off the substrate within a few weeks. And that produced what we call our spore powder or the Bavaria product and Mealworm product. We then check that for its quality by looking at its moisture content and its viability. So with our granular formulation being effective in the laboratory, we wanted to see if we could get some good results and some population control of lesser mealworm in the field. So we conducted a field study at Redland Bay, which looked at a Mealworm and a Bavaria granular formulation in comparison to industry insecticides, which was a rotation in this case of Elector and Prolong, spinosad and beta-cyfluthrin versus untreated. So we had 2 sheds per treatment, and we looked at those treatments continuously over a 5-batch period. We applied our granular formulation using a simple fertilizer spreader. As you can see in the pictures, the fertilizer spreader was applying the formulation only under the feed lines and along the walls where the majority of the population occurs of lesser mealworm. The way we measured whether we were getting effect was to look at numbers of lesser mealworms over time, each batch, each week. And so we took 10 litter samples across each chicken shed from designated areas from beneath the feed lines. We then took those samples back to the laboratory and counted the numbers of live lesser mealworms. The pictures here show the types of numbers that excuse me, we were encountering in the field. The sample there indicates that there are quite a few lesser mealworms. I think the most lesser mealworms we ever collected in one day and counted was about 72,000. So here are the results of the first field trial. You can see there the red line in the graph indicates the control populations. The untreated populations over 5 batches just continued to rise. There was no treatments, so the beetle numbers increased. If you look at the green and the blue line in the graph, that represents Mealworm and insecticide rotation, and you can see that they're much lower but about the same. The best of the treatments was the Bavaria insecticide, sorry, the Bavaria mycopesticide, and you can see there in the table below that on average it was ended up being 72% lower than the control. So I think that we, over the 5-batch period, indicated that there was definitely a proof of concept for fungal control of lesser mealworm. And you might see that little black arrow on the graph there. That just indicates where the chicken meat company applied a fungicide, and we had a little blip in the results there where they increased. So in our current study, which was funded basically on the back of our proof of concept for the first one, we decided to optimize our mycopesticide for lesser mealworm. What we were looking at was continuing to test the Bavaria formulation since it was the most successful in the first field trial. We wanted to test that under different litter regimes, a full litter replacement regime and a partial litter placement regime. Also in concrete and hard floored sheds, and test the fungus over the winter period to see if any seasonal effects had any effect on the efficacy of the fungus. In addition to the granular formulation, we want to test a liquid formulation because it's more in line with the liquid insecticide formulations that are currently being used with lesser mealworm in chicken sheds in Australia. In addition to those tests, we also wanted to look at the combination of mycopesticides with industry chemical insecticides to see if we could get a synergy, to see if with combined we could get a greater effect than either agent alone. And the main thrust of this particular study was to get a whole heap of data together to try and attract a commercial collaborator that can produce a mycopesticide for lesser mealworm control for chicken meat industry in Australia. So we've just completed a Twofarm study comparing the Bavaria granules in full litter and partial litter replacement meat chicken sheds. We compared that granular formulation to an insecticide regimen that consisted only of Prolong and to no treatment. As in the first study described earlier, we measured the populations by taking litter samples each week. So here are the results at Farm 1. Over 4 treatment batches, if you look at the top graph in the full litter replacement, you can see that the orange line is the Bavaria granular treatment, and you can see that numbers continue to decline over the batch period. The insecticide is a bit more variable. It went up and down, which was surprising. And the control had a strange little dip there, but again, numbers increased away over the time of the trial, which you'd expect. In the partial litter replacement, it was sort of similar. The Bavaria stayed quite low over the time of the trial and even dipped below the numbers that it initially was, whereas surprisingly, the insecticide increased away and the control increased away. So at Farm 1, we had very good results in both full litter and partial litter replacement with the mycopesticide. Now, Farm 2 was a different story. We found that there wasn't much difference between no treatment, insecticide, and mycopesticide in either the partial replacement or full litter replacement chicken sheds. So we were a bit perplexed by this, such a difference between the two farms. What we have, or what we know, is that at this farm number 2, the treatments of mycopesticide and insecticide were done about 2 weeks before the batch started, whereas at Farm 1, they were applied about a week before. So we're wondering whether this longer period before the batch starts has affected in some way the efficacy not only of the mycopesticide, but even of the insecticide, and it might be something to think about for future beetle control regimens. In addition to our field trial, we've looked at a number of different investigations in the lab to try and explain the results that we've gotten. We've looked at the effect of ammonia on the formulation and on the Bavaria spores in the formulation. We found that spore germination was not affected up to 350 ppm ammonia with 48 hours exposure in the laboratory. We did, however, find that spores were reduced by a small amount, 10% efficacy in the field, or germination in the field after 11 days exposure. But there could be other factors contributing to that, such as the high temperatures that can occur between batches when the shed's all closed up and the moisture content. We found that the granular formulation itself retained its efficacy despite 11 days exposure and despite this small reduction in spore germination. We found that in the lab and the field under those ammonia conditions. We also looked at the pH of the litter in these sheds. We found that there's a bit of variability in the pH of fresh wood shavings, which is probably not surprising depending on the age and type of shavings that goes in. But we found that they can range between 5.5 and 7.5, which is interesting considering that pHs of about 9 are probably considered optimum for ammonia production. So it might be worth thinking about sourcing fresh wood shavings that is either basic or more acetic in quality to try and keep ammonia levels down. And we found used litter to be about 8.5, which is getting close to that optimum ammonia production. But interestingly, we found that if we applied our granules directly to used litter in the laboratory, it didn't impede the efficacy of the Bavaria mycopesticide formulation. We also looked at the insecticide resistance of the field populations at the 2 farms. We found that that the insects were about 30 times more resistant to beta-cyfluthrin, the main ingredient in Prolong, than our laboratory population of lesser mealworm that has not seen any insecticide. And interestingly, there was no difference in tolerance or susceptibility to the fungi between field and laboratory populations of lesser mealworm, indicating no resistance whatsoever as opposed to beta-cyfluthrin. We also did a survey of floor hardness across all the sheds, and we found that loosely there is a correlation between the hardness of the shed floor and the number of beetles found in each shed, which is kind of in an anecdotal way already known, but now we have some data and we're working on correlating that now. Also, we've been doing our study looking at co-applications of insecticides and fungi for greater effect. When you combine those together, a fungus and an insecticide, you're looking for an effect greater than what you'd expect for either agent alone or even their combined mortalities. So when that happens, it's referred to as synergism. Most synergism is observed when an insecticide is applied before a fungus. And what is thought to occur is that the insecticide affects or physiologically stresses or modifies the behavior of the insect, which allows it to be more susceptible to fungal infection. Our early results indicate that if you combine beta-cyfluthrin and Beauveria, and the beta-cyfluthrin at 10 ppm, which was about a tenth of the rate of its field application, with a low rate of Beauveria, then we can get a much higher efficacy. The examples there that I've got, the larvae, we were able to get about a 70-odd% efficacy or mortality above the Beauveria and the cyfluthrin, which had about 15 and 10% mortality respectively. For beetles, the 10 ppm beta-cyfluthrin had no effect at all. And the Beauveria had a small effect, but together they had a close to 60% mortality effect. So there's definitely something in there, and it's quite an exciting piece of work. We're still in the preliminary stages of doing this work, but I think that there's definitely some potential there of combining these agents for greater efficacy. So where are we up to? Well, we just completed the field trial at those two farms, which I showed the results for, under partial and full litter replacement. So I think that our main achievement here is demonstrating that there is efficacy under those two litter regimens. We had some odd results at one of the farms, but we know that in the first study that we did a few years ago, and at one farm, we can get good efficacy. So I think that there are reasons behind the lack of difference between the treatments at one of those farms, at farm 2, and we're still trying to work that out. Our current research will be to commence a new field trial in the next year to look at the activity of the mycopesticide formulation on hard floored sheds, and to test a liquid formulation of the fungus. Once we get some data together, particularly after these trials that we've just completed, we're going to be putting out an expression of interest for a commercial partner to try and produce a fungal mycopesticide for chicken meat industry. I'd just like to thank everyone that's helped us do these trials, and our collaborators both in industry and the government and our funding bodies. Thank you.